Hi, everybody. So today I'm going to be sharing a little bit about wind farm design and simulation. So a little bit about me. I am part of the Flow Lab here at BYU, and we focus on design and optimization of both wind turbines, wind farms, and some flight vehicles as well. But I'm on the wind side. So a little bit about wind farm design. The process starts with collecting data about the site. Things like average wind speed and direction, as well as the geographical boundaries of where the farm is going to be. And here's just one piece of that data. This is called a wind rose. It shows both speed and direction that the wind flows through a given site. And we can use that data to kind of optimize the layout of where the wind turbines are going to go. So after significant data is collected about the site, then the next step is a low fidelity optimization of the wind farm. So generally, these are optimized to maximize energy production, but usually constrained with things such as the geographical bounds and costs, sometimes things like that. So this is just an example low fidelity optimization. So like this is the initial condition, and then based on things such as the wind direction, this is the final optimal layout of the wind farm, which with each of these small circles representing a turbine and the large circle representing the bounds of where the farm can go. And this low fidelity optimization was performed with a tool called Flow Farm. It was made by a different graduate student in the Flow Lab. Um, And here's what I'm talking about when I say low fidelity simulation. So there's no actual, um, well, there's very low fidelity simulation of how the aerodynamics are going to work in this farm and specifically how the turbines are going to influence one another. So here, all these turbines you see down here, or all these lines, these correspond to wakes uh, of the turbines in this optimal solution. So kind of the idea is you want the turbines to not be within the wakes of one another because if they're in the wake of another turbine, um, they're going to have lower performance, and also that adds to structural loading, and it's just generally not the best alignment. So up to this point, no supercomputing is needed. This is done on a laptop computer, often takes between 3 and 30 minutes. Um, it's not that intense. But after this low fidelity optimization is complete, then we move on to a mid and high fidelity simulation of that wind farm because sometimes you miss things with the low fidelity. So after that, we move on to a computational fluid dynamics simulator, or and in this case, I use a subset of computational fluid dynamics called large eddy simulation. And what large eddy simulation is, it's a way to um, simulate turbulence in that the largest eddies or vortexes, however you want to think of them, are simulated and the smaller ones are just modeled. So here, these are screenshots from a simulation I ran using a program called AMR Wind in conjunction with OpenFast, and both of those are developed by government laboratories. Um, so this is like the rotor view of a wind turbine, and this is the turbine's wake. And you can see it's got these tip vortices coming off here. Um, those come off the tips of the blades, and then later down the wake breaks up and just kind of becomes fully turbulent. So how mesh-based CFD and large eddy simulation works is basically you have a fluid domain. In my case, it's a box representing that, well, the area, the wind, the air around a wind turbine. And that box of fluid, your fluid domain, is broken up into smaller boxes called cells. And it's assumed that within those cells, within a given cell, the fluid properties such as velocity, temperature, pressure, anything else is constant. No matter where you are in the cell, it's constant across that cell, but it's different from cell to cell. So then what we do is based on the parameters, well, the parameters of the fluid within a given cell, we're able to calculate how the fluid in that cell is going to move to surrounding cells as time goes forward. So in this case, this is just a simple four cell visualization I have of like a basic vortex where fluid flows out of this cell into this cell, and fluid in this cell flows into this cell, and it continues and it makes a vortex or eddy. Um, so why is high performance computing needed to do this? Well, the number of cells in a given simulation is often, well, very large. So I pulled some statistics from a recent simulation I ran, consisting of two turbines. You can see one's located here, one is located here. The wind is blowing from left to right, and you can see the wake comes off of this upstream turbine, and then it meets this downstream turbine, and then their combined wake is very turbulent. Um, so this simulation here, it's in 3 dimensions. It's just a two-dimensional slice, but it consisted of roughly 61 million cells. And for some perspective, using 128 cores and 256 gigabytes of memory, it took about 49 and a half hours of wall clock time to simulate 5 minutes of turbine operation. So it takes a lot to simulate these turbines, especially with the large number of cells needed to do so accurately. So that's something else I wanted to talk about, the dilemma of computational cost versus accuracy. Because the more cells you have, and specifically the smaller cells you have, the more accurate the simulations will be. But that also increases your computing cost often very quickly. Adding more cells, adding smaller cells makes things take a lot longer. Um, so how can we reconcile these two that we want small cells but can't afford them everywhere? Is we just refine parts of the mesh of the domain, right? Where interesting things are happening. So in my case, this is the rotors, the turbine rotors itself, and their wakes. That's the part I'm interested in. So here I have a zoomed in screenshot of a mesh, same of the mesh of this same one that I was showing you before, the same simulation. So you can see further away from the turbines, the cells get bigger, and it's hard to make out the individual cells, but darker blue here means smaller cells. And you can see as I approach the rotor, um, the mesh actually gets much darker. That means much smaller cells. And if you might be able to make it out, you might not, but there are actually two very dark boxes around where the turbine rotors themselves are, and then this kind of darker box surrounding their weights. And then for perspective, here's the zoomed out mesh for that same simulation. Um, Very far away from the turbines. The cells are about 76 meters long. These are cubic cells, so one side length is about 76 meters, which is crazy big. And then as you move closer to the turbine, the cells get smaller and smaller, and at the turbine, the smallest cells are only about 0.6 meters long. So that's just the way we deal with computational cost and efficiently use our cells. That's all. So that's about all I've got, but I did want to show really quick the importance of having a good refined mesh. So I'm going to show you some images here of a mesh that gets progressively less fine, where the cells get bigger in the wake zone. So in this simulation, this is a single turbine run for 90 seconds. The cells in the wake are 0.59 meters, and then as I move up, now we have 0.79, 0.91, 1.8, 1.18, 1.82, and 2.36. You can see I've really lost some behavior. Just like you can see the tip vortices disappear very quickly because the cells are just too big to sustain them. And here we're getting finer again. This is just to show you the importance of having a fine mesh. And that's about all I've got. So thank you very much.